Hi guys, I'm Logan and this is Dean, and we looked at how air pressure affects the coefficient of restitution.
So the thing we were looking for really was, I'm going to preface this with, this was kind of a simple lab. We didn't really think about how fundamental this thing we were looking at was, but essentially what we were doing was we were looking at how much, or how the relationship between how much pressure is in the ball and how high it bounces was. And that's essentially the coefficient of restitution, which is kind of nice. We've done a lab about this, so getting all this data was pretty straightforward. We knew how to do it, and it was pretty simple to figure it all out. We thought that pretty intuitively, as you put more pressure in the ball, it'll bounce higher, and we didn't look at why that was, but we looked at what was happening there. This was our setup. We had Logan standing on top of the, what do you call it?
Robert's gym stands.
Yeah, he was up there, dropped the ball, had a meter stick, took a video, and we used Logger Pro a lot. It's kind of hard to see these little numbers here, but one is the ball. We were mistakenly using a Bowden ball to begin, and that ball broke about halfway through. So if you wanted to reproduce this, I would recommend not using that type of volleyball, because they're not very good. I hear that that's not an isolated incident. They're kind of the lowest end of volleyball. We used an air pump to pump it up. We used electric. You can use either type. Video camera, computer, meter stick, some basic physics stuff. The most important thing to use, though, was the air pressure gauge, and we actually had to get that from our volleyball coach. It's what allowed us to tell what the pressure inside the ball was, and it works like a tire pressure gauge, but it has the little spike on it, so you can stick it into a ball. Actually, I'm going to go back a little bit, because this is an important thing. You can see here that the ground looks like it's there, but it's actually sort of this way because of how the camera was angled. It wasn't actually on the ground. So this was something we had to deal with in Logger Pro, was the computer thinking it was on the ground when or thinking it was above the ground when it was actually hitting the ground. So a little perspective. Logan, you want to do this one? Sure, I didn't know.
So how we did this, we took video using my phone, and then we put it onto Logger Pro, and then we did video analysis, and we graphed the ball's position versus time. We made a graph. We made it for 9 trials, I believe.
That's a lot.
Yeah, there's a lot of graphs. We were going to do kinetic energy and potential energy, and then stuff went wrong and it was bad.
Is that it? Okay, yeah. This is just a look at some of the data we collected. We based the table for this off of the data for the lab we had done with coefficient of restitution beforehand, and that worked out pretty well for us. We didn't actually need all of these numbers, we found out about halfway through, but we had gotten most of them, and we just filled out the table. This would also allow you to look at things like kinetic energy and stuff. Yeah, this was our result. This was the big graph. It has air pressure plotted on the y-axis. That's in pascals, which is an annoying unit to use for this because usually people use kilopascals, but pascals is the SI unit, and these are like thousands of pascals. Like 25,000 is the top over there, and it's just crazy big. And then coefficient of restitution over here, which is less than 1, which made the slope ridiculous also. You can see that it's, 170,000, which is kind of strange, but it was pretty linear, and that was a beautiful thing for us because that's sort of what we hypothesized, is like you put air pressure into the ball, how high it bounces goes up, and that was a very straightforward relationship, which was cool to look at. And there's some more stuff that we'll talk about with this graph a little later. Logan, take this one. Yeah, sorry.
Oh, yeah, so we found from our data that the coefficient of restitution and the air pressure in the ball are directly related. They are. So as air pressure goes up, it bounces higher. Correlation is 0.9162, which is pretty insane.
Yeah, a correlation of 1 basically means that all of the points were on the line, and 0.91 is pretty close for a linear relationship. So that was exciting information to see, like, oh, we got it pretty good. And that's with all of the error that we could have had in either direction, which was fun. These are some sources of error. obviously we talked about the floor being weird in the video before, and that was a problem we ran into because we weren't using a motion sensor. We were taking videos and doing video analysis in Logger Pro. Obviously, when you're working in the real world, not thinking about error resistance will be error in the experiment. Error. Little funny joke there. It wasn't too bad though, because the ball's pretty small, and it's not like the coffee filters where it had this huge like umbrella of stuff. It went through the air pretty nicely. Our ball broke halfway through this experiment, and instead of taking all new data, which it was like all at the half point, we got a ball that was almost identical, but it wasn't the same ball. So that was a small source of error, and if we had used the same ball, we could have probably chopped off a few percentage points of that error, but we felt like it really didn't matter that much because like a volleyball's a volleyball, especially because of how closely regulated they are by Misha and everything. So that could have been a source, but not really. Another big one was that in any gym with a hardwood floor, you're going to have some weak spots in the floor, and so the density of the floor, which is sort of how coefficient of restitution affects the ball's bouncing, can vary depending on how you drop it and where you drop it and all of that good stuff. And then of course, we're people, we're humans, we make mistakes, and when we're doing video analysis, you have to click the center of the ball like a million times, and sometimes it's not exactly the center. So that was another huge source of error for us. And when I say huge, I'm talking about like 2 or 3%, not like hundreds of percent error, because that would be a little ridiculous. Our conclusion was essentially that the ball bounces, and how much air pressure you put in it directly affects the coefficient of restitution, which was cool. And in this paragraph, we sort of talk about how this isn't something you really think about a lot, because as like from the time you're a little kid, you're bouncing balls on the ground, and you immediately know that like if you don't fill it with air, it doesn't bounce as high. So it's interesting to go beyond that, like this happens, and look at like what's causing that to happen, and really take a systematic approach to finding out how and why and to what degree that happens and all of that. There's another thing we found though that is a little fun, or at least I thought it was fun, and it comes from the orientation of these axes. You'll notice that all the way at the far that side, I don't know if it's right or left for you guys, it's not 0, it's around 0.7 over there, and so that means that there's going to be an intersect at some point that's not shown on this graph, and we can calculate that intersect. It's on the x-axis. It's important to notice that. On the y-axis, the intersect is at a negative value, which we had to disregard completely because that would have shown where the coefficient of restitution was 0, and that would mean that no energy from the floor was transferred back up into the ball to make it bounce. And that just doesn't happen. You have to have a negative air pressure for that to happen, as shown by our data. But the interesting thing was the x-axis, the intersect with that is where the air pressure is 0. And so that means, like, if you drop something like a rock or a brick on the ground, where it's not inflated and it doesn't have that springiness to it, that's the coefficient of restitution where that'll bounce, or at least that's what we inferred. And we found that number to be roughly 0.65, and I thought that was super cool because you could then do tests to see like, oh, if we look at how a brick bounces, because bricks do bounce, rocks do bounce, they just don't bounce very well. So I thought that number was super cool. And that's the end of our presentation.
One question, time for one question.
Okay, so you've got that nice line there, right? Can you go back to that?
Oops.
Okay, so I presume eventually that line would hit 1 on the x-axis, where it's got a 1 coefficient of restitution, which would be what, a really high air pressure?
Yeah.
Too high for the volleyball.
So
The
that
ball
would be
would-
where it would lose no energy in a bounce?
Yeah. From what I understand about coefficient of restitution, having a coefficient of 1 would mean that you drop the ball and it comes back exactly to where you dropped it. And in the real world, that's not possible because the ball will always lose energy when it hits the ground in the real world. Like sound, vibrations, heat, all of that good stuff that we try not to consider at this level of physics, that stuff all happens. And if you remember the slap contest, the guy who was talking about glasses kind of touched on that. When you drop a BB on a metal surface, it dents the surface and you get that like energy loss, but when you have the glass, it doesn't go quite as high, but it never reaches 1 as far as I know. And experimentally, I do not think you could reach a coefficient of restitution that was exactly 1. And obviously you couldn't go higher than that, because then you would be dropping the ball from here and it would bounce up to here and then it would bounce up to there, and that would be ridiculous.
I was just wondering, like, if you pretended that there was nothing else that would interfere with it, how absurd is the number of air pressure, like the amount of air pressure that you need to have in the ball?
That is not something that we looked at, but to give you a reference point, the coefficient of restitution at 0.8 looks to be about 25,000 pascals, which is kind of a lot. Like, the ball breaks at a certain point. I don't remember the number. We didn't look at that either because we were just saying, oh, we won't fill it up too much.
We were getting pretty close to it exploding, though.
I think at around 3 kilopascals, the ball pops and you no longer have that container for the ball. So yeah, you could get it to a pretty high air pressure and it would still go up and up and up. And I'm not sure exactly the relationship as it approaches that 1 or as it approaches 0. Those could have different effects, but the range we were looking at with normal air pressures for balls, like what we would consider flat and like fully filled, that was what we were really looking at in this experiment, and we found that relationship to be very linear. I hope that answers your question.
Cool. Thank you, guys.
Fundamental this thing we were looking at was, but essentially what we were doing was we were looking at how much, or how the relationship between how much pressure is in the ball and how high it bounces was. And that's essentially the coefficient of restitution, which is kind of nice. We've done a lab about this, so.
Hi guys, I'm Logan and this is Dean, and we looked at how air pressure affects the coefficient of restitution.
So the thing we were looking for really was, I'm going to preface this with, this was kind of a simple lab. We didn't really think about how, like, getting all this data was pretty straightforward. We knew how to do it, and it was pretty simple to figure it all out. We thought that pretty intuitively, as you put more pressure in the ball, it'll bounce higher, and we didn't look at why that was, but we looked at what was happening there. This was our setup. We had Logan standing on top of the, what do you call it?
Robert's gym stands.
Yeah, he was up there, dropped the ball, had a meter stick, took a video, and we used Logger Pro a lot. It's kind of hard to see these little numbers here, but 1 is the ball. We were mistakenly using a Bowden ball to begin, and that ball broke about halfway through. So if you wanted to reproduce this, I would recommend not using that type of volleyball, because they're not very good.